All right, this problem is from section 4.7, optimization problems, which are a pinnacle of what you do with derivatives in calculus. And we're trying to find the best way to do something, and this one involves a paper drinking cup. So that's a paper drinking cup, like the kind that you roll the paper and makes the cone shape. And the cone shaped paper drinking cup is to be made to hold 27 cubic centimeters of water. Like you pull off one of the Home Depot or Lowe's drinking container things, big jugs, and you fill it up, and then you don't want to waste a lot of paper, so you want to make this be the minimum amount of paper and hold 27 cubic centimeters of water. That's like a couple of nice gulps of water. Find the height and radius of the cup that will use the least amount of paper. So when you do an optimization problem, you're always trying to do something the best way, or best way either by minimizing something or maximizing something, and calculus helps us find those mins and maxes precisely. All these problems are the same. It's just that how you deal with the equations is going to be different. Every problem is a little different because you have different equations. But the main parts are the same. So there's going to be some kind of helper equation, and then there's going to be some kind of governing equation. And our governing equation is surface area, because we want to have the smallest amount of paper here. But our volume is equal to 1/3 pi r squared h, and that's 27. So that's my helper equation, and I can solve for h, I can solve for r, and then plug it into a different equation. The surface area of a cone is something that's not readily known. You can look it up, look that up in any book, and that's pi r square root of r squared plus h squared. So that's the lateral surface area of the cone. It doesn't include the circle there, but it's the lateral surface area of a cone. So we can solve for r and put it in here and here. We can solve for h and put it there. It's a little bit easier to solve for h and put it into there instead of solving for r and having to put the two substitutions. But we have to make this into well, it's a lot easier if you make it be one variable for the input and one variable for the output. So as we have h and r, we want it to be all in terms of r. Makes it a little bit easier to deal with. Okay, so what is h? So I'm going to multiply the 3 over, so 81 is equal to pi r squared h. So I multiplied the 3 over, and then I'm going to divide over the pi r squared. So divide by pi r squared, divide by pi r squared. So h is equal to 81 over pi r squared. So now I'm going to substitute that in there. So I'm going to go ahead and square everything. So I'm going to do h squared. So h squared is what I'm really substituting in for. So I need 81 squared. So I got 81 squared is 6561. So it's 6561 over pi squared r to the 4th power. Voila. So now I'm going to do area. The surface area of my cone is pi r square root. Now I'm going to do that to the 1/2 power. So get my nope. Looking for my whiteout. What did I do with my whiteout? Oh, there it is. Found it. I'm going to change this to the 1/2 power because I think it's easier to think about the derivative. So it's going to be r squared plus h squared. And what's h squared equal to? 6561. 6561 over pi squared, and then r, I'm going to bring that up to the top because it's easier to take the derivative. So I'm going to think of that as r to the negative 4 to the 1/2 power. Okay, so this one in here, I brought the r to the 4th up to the top because it's easier to take the derivative that way, and I also made that be the 1/2 power. So now I'm going to enact the product rule, because this is the derivative of the first times the second, derivative of the second times the first. So surface area prime is derivative of the first, pi, that was easy, times this, r squared plus 6561 pi squared r to the negative 4th to the 1/2 power, plus derivative of the second. The 1/2 comes down to the front, so it's 1/2 blah 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 to the negative 1/2 power. And so I put in my r squared plus 6561 over pi squared r to the negative 4th. Okay, times the derivative of the inside. Derivative of the inside would be 2r, and then we got to do negative 4 times that, so it'd be negative 20. I already multiplied it out here. 26,244. 26,244. 26,244 over pi squared. So we do negative 4 times this, and then you got to subtract 1, r to the negative 5th. So it's this comes, so the derivative of this here is this comes down here, subtract 1, derivative of the copy that down. Derivative of the inside is 2r, negative 4 times the front, subtract 1, and then times the first, so I need times pi and r. I think I need to back this up a little bit higher so I can see the whole derivative across the screen. So that's the whole derivative right there. Okay, so this here doesn't change at all. It's just r squared plus 6561 over pi squared r to the negative 4 to the 1/2 power. Now I'm going to make this into a fraction here. So the half goes to the bottom, crosses the line, changes sign, the 2 does, and the rest of it stays on the top, so it's 2r squared plus 6561 pi squared r to the negative 4th to the 1/2 power. And then we need to distribute this times this, so we distribute this through here, so that's 2 pi r squared, and then I'm going to distribute this times this, so that's still going to be negative 26 244. Now the pi's are going to cancel, so there'll be 1 pi on the bottom, and then that, when you multiply like bases together, you add the exponents, so it's going to be r to the 4th. Negative 4th. Okay, I'm going to pause here for a second. Okay, I thought I did something wrong. I was checking before I went on, double checking my work here. But I'm okay, I'm okay. So I got this times this is this, this times this is this. Alright, so I'm going to get a common denominator between these two. I'm going to put some purple pin in here. This one has a 2 and this one doesn't, so I need to multiply the top and the bottom by 2. This one has a r squared plus blah blah blah, that's a 1/2 power, so I need one of these over here. R squared plus 6561 over r squared r to the negative 4th to the 1/2 power. Okay, so if I put one of these on the bottom, I need one on the top, which is exactly what this is. And if you put 2 of them on the top and you multiply them together, you're going to get 1/2 power times the 1/2 power is going to be 1. So there's really just the 1 power there. Now I can distribute this through the parentheses. So I get 2 pi r squared, 2 pi r squared, and then there's a plus sign there, and then this times this, so I need to multiply this thing by 2, and then the pi's will cancel. So I get 65, 61 times 2, 65, 61 times 2, 13, and it's half of that, so that's good. 13, 122, so plus 13, 122. The pi here will cancel with this pi here, squared, so there's a pi on the bottom, and then it's r to the negative 4th. So this times this is this, this times this, that doubled, the pi's cancel, I got this, plus common denominator, 2 pi r squared minus 26, 244 r to the negative 4, all over the common denominator, 2 r squared plus 65, 61 pi squared r to the negative 4 to the 1/2 power. Okay, so we have this down here. Now we're looking for the critical points on this. This looks incredibly complicated, but it is going to fall apart here in a minute. So this is, don't lose sight of what we're doing here. This is the derivative, and we're going to set the numerator and the denominator equal to 0 to find the critical points. Now, just to speed this up, setting the denominator equal to 0 is not going to create the solution. It'll come from the numerator set equal to 0. So collect our like terms. We got this and this. It'd be 4 pi r squared, and then this and that are half each other, so it's going to be minus 13, 122 r to the negative 4th over pi is equal to 0. So here's where it starts to fall apart. So that plus that, okay, this plus this makes this, and then I put those two together. Oops, I lost a pi right there, didn't I? Okay, and I'm going to pause again. So I'm going to finish this off real quick here. I'm going to bring this to the bottom and make this r to the 4th, and then I'm going to get a common denominator between these two. So I need an r to the 4th down here, which means I need 4 r's on the top here, so that's now 6. And then I need a pi over here, right? So then the answer is going to come from not from here, because R0 would be definitely a critical point because there'd be no radius at all. The answer is going to come from setting that part equal to 0, which is 4 pi r to the 6 minus 13, 122 equals 0. So I'm going to subtract that over, divide that over, so r to the 6 is equal to 13, 122 over 4 pi. Then to get r by itself, I'm running out of paper here. I've got to take the 6th root of each side of the equation, and that's my answer in centimeters. So I'm going to do 13, 122 divided by 4 divided by pi, and I get this answer right here. And then I have to take the 6th root of it, so I'm going to raise it to the power of 1 divided by 6. Answer 3.18. And I got a different answer this morning. Got a little different answer this morning, so let me check and make sure what I did wrong here, or right. Okay, found my mistake. When I got my common denominator here, I multiplied this by pi, multiplied this by pi. I forgot to multiply the top by pi, so that should be pi squared. So that means this is pi squared, which means this is pi squared. There we go. So I had to get a common denominator here, so I need to multiply the top and the bottom by pi, and the top and the bottom by r to the 4th. So then I have this answer right here. So it's the 6th root, math, root, 6th root, push myself through, 13, 122, divided by two things, so put that in parentheses, 4 second pi squared squared, parentheses. Now, there we go. 2.63. So 2.632. Okay, and there's the answer to that. So these are not all the same, but they are kind of the same, where there's going to be a helper equation, and then there's going to be a governing equation. And you always put the helper into the governing, and how do you tell which is which? Well, it says find the smallest amount of paper. So area, the surface area of the cone is your smallest. Here's your governing equation. Sorry, here's your governing equation. So then you put this into here, get it to two variables, one input, one output, take the derivative, set it equal to 0, right? Keep working through and do that. Now these problems are not all this challenging and messy with the algebra, but that can be done. All right, peace.